A pulley is something that we see pretty frequently, and pulleys are grooved wheels. So you can see on these pictures that there is a line in the center of our wheel that usually has a rope or a string of some kind that goes over. So it's this grooved wheel that serves as the pulley part. And they really only change the direction of the force. If you have one pulley, it's just pretty much going to change the direction of the force. However, we can see that by adding pulleys, so the more pulleys you have, so that you can see this one has one, this pulley has one pulley here, and there is a force of 100 newtons that is applied to lift this weight. But when I add a second pulley, now my force is only 50 newtons. So the more pulleys you have, the more you can actually decrease the force of the object. But the reason that decreases is because now my string has traveled a much larger distance. Instead of traveling 10 centimeters, now my string has covered 20 because I had to go down the one and then up over the other. So a larger distance equals a smaller force. We have two different types of pulleys. One is called a fixed and the other is a movable. A fixed pulley does not move with the load. So up here at the top, we've got the fixed pulley. Notice the string is going to move, but the location of the pulley is not going to move. These do not change the direction, these change the direction of the force, but does not change the amount of force or the size of the force required. So fixed pulleys change the direction of the force, but not the size or the amount. A movable pulley, on the other hand, is attached to the load. And these do not change the direction, they change the size. So on your paper you should have a movable pulley. It is attached to the load, so it moves with the load. And movable pulleys change the size of the force, but not the direction. Movable pulleys change the size of the force, but not the direction. So this one you can see is a movable pulley here. I still have to pull up to get the object to move up. This one down here, notice the string is going to move up and the load is going to move up. So this is actually a double pulley system, whereas this is a single pulley system. And this one's movable and this one's got a fixed pulley and a movable pulley. So some examples of pulleys are going to be cranes, those things that they use on construction buildings, flagpoles. So here you can see we've got a flagpole without the flag on it. There is a rope that moves the flag up and down that allows you to, it's a pulley system that raises the flag. Window blinds, that you pull the string and it lifts the blind up. Elevators, the weight moves down and it pulls the elevator up. So anytime you have things moving up and there's probably a rope attached, it's going to be a pulley system. So pulleys mostly change the direction of the force, but the more pulleys you add, the more it's going to change the size. So let's look at another super common kind of simple machine called an inclined plane. These inclined planes are sloping straight surfaces. And it makes it easier to move an object because it's increasing the distance the object is moving. So the longer the ramp, or as the length of the plane, as the length of the plane increases, so the longer the ramp length, the less force is required. So the longer the ramp length, or as your plane increases, the less force required. The longer your ramp, the less force is required. So the force required decreases. However, we're always going to have the same amount of work because you're never going to get less work out of a machine. When we're talking about simple machines, we're not talking about reducing the amount of work. We're talking about making the work easier. And we make the work easier by adding or by reducing the force and adding distance. But it's always going to be the same amount of work because of friction. It's always going to be the same amount of work because of friction. So let's talk about some examples of inclined planes. You can have stairs. Those are an example. A ramp, slides. Please notice that it looks kind of like a triangle. So we've got, this is the plane part of it, and we're going up a distance. In this case, we're moving it something down a distance, usually a ladder. Notice that they all have that triangle shape. Notice that triangle shape. Triangle shape. One of the ways that you know you have an inclined plane is that we're moving objects up it and it has a triangle shape. A wedge is very, very similar to an inclined plane, as these are two inclined planes that are attached, or a double inclined plane, but these move, whereas most of our inclined planes are going to be stationary. You don't want a ladder to move when you're climbing on it. That's really dangerous. You don't want stairs to move while you're climbing on them. That could, like, if they move away, you could fall and hurt yourself. But but wedges are designed to move because they are used to cut things or to pin things together. And so we see that the longer the blade, or the longer the inclined plane is, the less force you have to apply. So the longer the knife, because that's an example of an inclined plane, the less force you have to use. So if you were to try and cut a watermelon with a teeny tiny knife, it's going to take a lot more effort and force than if you were to use a very long, sharp chef's knife. So some other examples of wedges are the head of the axe, not the body of the axe, but the head of the axe. A push pin, notice it's got that pointy edge and it cuts through paper to then hold them together. A safety pin, because it cuts through the clothing to hold it together. Those are all examples of wedges. A screw is also related to an inclined plane, except this is an inclined plane that's wrapped in a spiral. So notice that they have tried to show you what a screw looks like using a piece of paper. So we've taken our inclined plane and a metal core, and as we wrap it around, do you see the threads that have formed, how it looks similar to a screw? That is exactly what a screw is. It's just an inclined plane wrapped in a spiral. And so we have a lot of different examples of those, but let's talk a little bit more about how it works. So we see that the more threads you have, or the closer together your threads are, the more force that is actually end up being applied. You don't have to use, so maybe you use 10 newtons of force on the screw, but you get 20 newtons of force out because it's going over such a large distance that you actually end up using less force. So the more threads, less force you have to use, the more force you get out of your machine. So some examples are jar lids, bottle caps, traditional screws, a spiral staircase, because it's an inclined plane wrapped in a spiral. So we see that they're used pretty frequently to hold things together, or to fasten things typically. So those are the 6 different types of simple machines, and we can actually compare them and evaluate them based on what they do for us. And the way we do that is using something called mechanical advantage and mechanical efficiency. So let's talk about mechanical advantage first. It's a comparison to see how good your machine is. And so the first thing we need to talk about is the input force. The input force is the force that you apply to the machine. It's the force that's applied to the machine. So on your paper, write that the input force is the force you apply to the machine. The output force is the force that the machine exerts or uses. So this is what you get out of the machine. It's the force that's applied on your object. And so mechanical advantage relates those two by telling us it's how many times the machine multiplies the input force. So if I put in 2 newtons of force in the machine, how heavy an object can I lift? How much force will I get out of the machine? So it's how many times the input force is multiplied by the machine. Please take a minute to pause this video and write down this equation. This mechanical advantage equals output divided by input. It's really important. The other way that notice we're still talking about mechanical advantage. There is no units for mechanical advantage because force is always measured in newtons. So these guys ends up canceling each other out. So mechanical advantage is just a number. So my machine is going to have a mechanical advantage of 1 or 2, meaning I get 2 times the force out of it. If your mechanical advantage is less than 1, then it is not a good machine. You're going to wind up putting more force into the machine. It's going to make your work harder, and it's not something we want to do. We always want to make the work easier. We want to use less force. So if your mechanical advantage is less than 1, it's probably not a machine we're going to use. And the other way that we rate our machines is with something called efficiency or mechanical efficiency. It's how well the machine uses the energy or the work I put into it. So when we're talking about efficiency, like you may have heard me refer to you guys as working efficiently or not. So an efficient science student completes their work on time and is focused and is not doing other things. Somebody that is distracted or socializing or working on math homework in science, they're not working efficiently because they're not using the time and the energy on science that we were putting in. So we can say the same thing with machines. An efficient machine uses the majority of the energy or the work put into it. And we have a formula that relates that. Please notice it is multiplied by 100 because efficiency is written as a percentage. So take a moment to pause this video and write down this equation. We see that machines are never 100% efficient. This is because of friction. We are always using some of the energy and some of the work to overcome friction. As you've increased the distance that the object is moving, then we're going to have more friction because you're going to have more contact between the surfaces. So some of that energy that we put into the machine has to be used to overcome friction. But we can reduce, sorry, I'm trying to find that problem. So when we multiply those two, so when we multiply 30 by 9.8, we find out that the force needed to move this object is 294 newtons. So if I know my force and I know my distance, I can multiply them together and I can figure out my work. So 294 times 0.4 is 117.6 joules of work. So that pulley did 117.6 joules of work. Let's look at mechanical advantage. So what is the mechanical advantage of a lever that gives you 10 newtons of force output after you've put 2 newtons of force into the machine? So I'm going to put my output first, which was 10, and I'm going to divide that by 2. Pardon my handwriting. 2 newtons. 10 divided by 2 is 5. So this machine has a mechanical advantage of 5. Notice there are no units because the units cancel. If a wheel and axle has a mechanical advantage of 2, how much force would you get out of the machine if you put 10 newtons of force into it? So we need to rearrange this equation. And we see when we do that, because I'm trying to get output force by itself, so then I have to first get rid of the input force, and so I do that by multiplying both sides by the input. So we get the mechanical advantage times the input is equal to the output. So we should have 2 times 10 equals 20. So I should get a 20 newton force out of the machine if my machine has a mechanical advantage of 2. I'd say that's a pretty good simple machine there. What is the mechanical efficiency of a screw that uses 300 joules of work, of input work, and, I'm sorry, let me read that. What is the mechanical efficiency of a screw that uses 300 joules of the input, 500 joules of work? So that means I got 300 joules out of the machine after we put in 500 joules. So I'm going to divide them. So output goes on top, divided by the input, which was 500, and we multiply that by 100. So 300 divided by 500 is 0.6 times 100, because order of operations here, people, So we see that this machine was 60% efficient. Not too bad. Not too bad at all.